Hello everyone, I am Devrata Swai and I have completed this project under Pregrad's Artificial Intelligence and Machine Learning course mentored by Saurav Sir. The project I made is credit risk modeling where I used machine learning to predict whether a loan applicant will get his loan or not, means his loan application will be approved or get rejected. My experience with Pregrad and Saurav Sir is very extremely valuable. This course was very well structured and practical. It is not only strengthened my fundamentals but also gave me real project exposure that boosted my confidence in AIML. Let's start my presentation. Hello everyone. Today we are going to work through a complete machine learning project focused on loan detection. We will start with the fundamental step that every data scientist does: exploratory data analysis or EDA. First thing we do when we get a new data set is to understand its structure and contents. We are importing necessary files like pandas for data manipulation, numpy for numerical operation, matplotlib and cbon for visualization, and we are also suppressing warning to keep our output clean. Now we are loading our loan detection dataset from an Excel file. Then the first thing we do is the print the entire dataset here, like you can see in the terminal. Wait, it will take some time to run as it is a very long code. These all are graphs. We will discuss it later within our presentation. Okay. First of all, you can see we printed all the columns and rows in our loan detection Excel file. Then uh, then we check the shape of our data here. Uh, this tells us how many rows and columns we have. Like you can see, this Excel sheet have 41188 rows and 60 columns. Uh, we examine then next we examine the column names to understand what variables are available. Like you can see here, print loan dot columns, and we get in the terminals the names of all 60 columns we have. You can see. Then we used info function, which is particularly useful because it shows us the data types of each column and whether we have any missing values. Like you can see here, mm, the info column, we get the data types of each column, whether we and you can see age data type is integer, and no null count means it is not a null column. So this will tell whether the column is null or and the data type of the column. And finally, the describe function, it gives us statistical summaries like mean, median, standard deviation, and quantiles. Like you can see here, as I have printed that 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 count, mean, standard deviation, like all the quartiles, 25%, 50%, 75%, and maximums. So this is all about describe function. This helps us to understand the distribution and range of our data. Next, let's talk about something crucial in classification problems: imbalance data. In real-world loan datasets, typically very few default on loans compared to those who repay them. This imbalance can bias our machine learning model. We were looking at the loan status level column, which is our target variable. When we use value count function here, here when we use the value count function, we can see how many examples we have for each class. Like loan is approved or not. Means in binary, if the loan is approved, it will be denoted as 1, and if loan is rejected, then it will be denoted as 0. Okay, you can print here as sorry, as I have printed here. You can see there is 36548 zeros and 4640 ones. Then we calculate the relative frequency. Here you can see we calculate the relative frequency for both the classes. This percentage tells us the proportion of each class in our dataset. If one class is significantly underrepresented, means for example 20% of one class versus 80% of the other classes, we have a serious imbalance problem. Our model might simply learn to always predict the majority class and still appear accurate. As you can see here, by printing the value count, as we can see clearly that 0 have 3, 6, 5, 4, 8 rows, and only 4, 6, 4, 0 rows have 1. It means 0 is in majority. So if we count it without relative frequency, the majority will win, and our model will give on the basis of majority. Means the chances of getting 0 will be more without checking other aspects. uh, understanding the imbalance is critical because we need to handle it carefully during model building, either through resampling techniques or by adjusting our evaluation matrix. Now let's address missing data. In real world scenarios, data sets are rarely perfect. Some values might be missing due to data collection error, non-responses, or various other reasons. We use isnal.sum to count missing values of each column. This tells us the absolute number of missing entries. Like you can see here, uh, you can see here, the we don't have any missing values in any of our columns. So then we calculate the percentage of missing data using isnal.mean into 100 or star 100. I know you are thinking about, if there is no missing columns, then why are we using this mean method and all the stops inside the for loop? Because we in this particular sheet there is no null columns, but if we use the model on other data set, then there can be missing data. So here we written all these stops inside the for loop. Then this is null dot mean. This percentage help us to decide whether the missing data is minimal and ignorable, or substantially enough to require special handling. For columns with missing values, we need to understand the data better. We calculate the mean and median of column. These statistics are important because the choice between them depends on whether our data is normally distributed or skewed. The mean is sensitive to outliers, while the median is robust. As you can know from the word itself, outliers, that that value which lies completely outside the box, means the value of that means the value is more distant from the other values in that column. Now here we visualize.
Now we also visualize the distribution using the distribution plot. This visualization is crucial because it shows us the shape of data. If the distribution is heavily skewed, imputing with the mean might not be best choice. Median or mode might be more appropriate. If no columns have missing values, as like in our data, that our data is complete. Otherwise, we need to decide on an imputation strategy based on the domain knowledge and the nature of the missing data. So here, outside the for, as I said, here we counted the miss, and if miss equal to lane of loan dot columns means, here we can say that if missed means that if there is no there is no null columns, then the code will print there is no missing data. Here we can see all are zeros, so in terminal there is showing there is no missing data. Then let's move to the next data quality issue: duplicate records. Sometimes the same record can appear multiple times in dataset due to data entry errors or system glitches. We use loan.duplicate.sum to count how many duplicate rows exist in our dataset. If we find duplicates, we can examine them using duplicate function. Like you can see here, here we have printed how many duplicates are there. There are 2417 duplicate rows. So we have also printed which are duplicate rows. Here you can see. So uh, once we have identified duplicates, we remove them using drop underscore duplicate function. And then the keep equal to first parameter tells Python to keep the first occurrence of any duplicate record and remove the rest. This makes sense because the first entry is typically the original record and the subsequent duplicates are likely errors. Removing duplicate is essential because having duplicates record can artificially inflate the importance of certain patterns in our data, leading to biased model training. Now we are entering a critical phase: handling outliers and anomalies. Outliers are data points that deviate significantly from the normal pattern. They can arise from the measurement errors or present genuine but rare phenomena. First, we create a box plot of all features. A box plot visually represent distribution of data using quartiles. The box shows where 50% of the data lies. The line inside shows the median, and the whiskers extend to show the range of typical values. Point beyond the whiskers are considered as outliers. Typically, you can see I have silenced all these because there is 60 columns. So in this for loop, we will print 60 graphs. The spam will make you restless. So I have been commented this. But if you want to see all the graphs, you can get all these stuffs in my submission section. So then, typically people use interquartile range IQR method for outlier detection. However, as noted in code comments, if your data is skewed, which is common in financial dataset like loans, the IQR method can be problematic as it might remove too many data points or important variations. Instead, we are using percentile capping, a more conservative approach. We set the lower and upper bound. We set the lower and upper bound at the 5th and 95th percentiles respectively. This means we cap the extreme values at this percentile while keeping all the data points in the dataset. No data is lost. We are only adjusting the extreme values to be less extreme. Like for age variable, we cap between 5th and 95th percentile for variable like campaign and previous. Here for variable like campaign and previous, uh, which is naturally have a lower bound of 0 and 1, we only cap the upper bound at 95%, 95th percentile. For binary variable, we can simply ensure they are kept between 0 and 1. This approach is especially important in the loan detection because every data point represents a real person's financial situation. So we can't afford to lose the data unnecessarily. And pay data don't need capping as it is not an outlier, but it is special encoded value, meaning client was never contacted before. Other columns are mainly binary, hence we will cap them as lower 0 and upper 1. Here in the for loop, we done that. Moving forward, we need to understand which features are most relevant for predicting loan status. Okay. This is called feature selection. Too many irrelevant feature can confuse our model and reduce its performance. We start by calculating the correlation matrix of all variable. Correlation measures the linear relationship between two variables, ranging from -1 that denotes perfect negative correlation to +1 that denotes perfect positive correlation. A correlation of 0 means no linear relationship. In this heat map, we visualize the correlation matrix as a heat map. This color intensity shows the strength of correlation. Maybe darker color indicates the stronger correlations. It may be positive or negative. This visual representation makes it easy to spot which features have strong relationship with our target variable. First of all we printed all the correlation, like you can see here. We printed all the correlations that ranging between -1 to 0. And here and here we we especially look at the correlation between all features and our loan status level, that our target variable. Featuring features with high absolute correlation values are more predictive of whether a loan will be approved or rejected. Features with correlation near 0 might be very useful for prediction. Based on these, as we have printed all these, and you can see in the terminal the correlation between loan status level and all the other columns. Okay, then based on these correlation, we could remove features that don't correlate well with our target. This reduce noise in our model and can improve both performance and interpretability. Remember, not all features with a high correlation are equally important. Some might be redundant if they are highly correlated with each other. Now we are entering the model building phase. This is where machine learning actually happens. But before we build any model, we need to prepare our data properly. First, we separate the dependent and independent variable. The dependent variable is what we want to predict. In this case, loan status level is the dependent variable. Like we have here, we differentiated the dependent variable and independent variable, where we assign the independent variable to the x and dependent variable to the y. Next, we split the data into training and testing. Here we printed x and y, you can see. Then we split the data into training and testing sets by the help of module sklearn. And we use 80% of data for training and reserve 20% for testing. This separation is very crucial because the model learns from the training set, but we evaluate it on the test set to get an unbiased estimate of how well it will perform on new unseen data. We use here we use random state equal to 42 to ensure producibility. If someone else runs this code, they will get the same split. Finally, we apply feature scaling with standard scaler. Different features have different ranges. For example, age might range from 20 to 80, while some binary features are just 0 or 1. Machine learning algorithm, especially those based on distance matrix like logistic regression and neural network, can be misled by these different scales. Standard scalar transforms each feature have a mean of 0 and a standard deviation of 1. This puts all features on the same playing field. Importantly, we feed the scalar only on the training data, then apply same transformation to the test data. This prevents data leakage where information from the test set inadvertently influences the model. Here we printed the skilled train and test models, train and test sets. Sorry, here we splitted, and we printed also the split X test, Y train, all the stops here. Then we printed. Mm, then we printed all these extrain and extrain SC and extrain X test SC means scaled extrain and X test sets. Now comes the exciting part, selecting and training machine learning models. We are going to compare four different algorithms to see which one performs based on our loan detection problem. First of all, logistic regression. Despite its name, this is a classification algorithm, not regression. It uses a sigmoid function to output probabilities between 0 and 1. It's simple, interpretable, and works well as a baseline. We feed it to our training data and check both training and testing accuracy. If training accuracy is much higher than the testing accuracy, then the model might be overfitting. As we have printed all the training and testing accuracy here, we can see logistic regressions, training and testing accuracy in the terminal. The second, decision tree. This algorithm creates a tree-like structure of if-then rule. Means if this will happen, then that will happen rule to classify data. It's highly interpretable. You can follow the decision path to understand why the model made a prediction. We set max depth equal to 6 to prevent the tree from becoming too deep and overfitting. Decision trees are powerful but prone to overfitting, which is why we limit their depth. We can see our decision trees training and testing accuracy here in the terminal. Third, AdaBoost. This is an assemble method that combines multiple weak learners into a strong one. It works by training multiple simple models sequentially, with each subsequent model focusing more on cases that previous model misclassified. This iterative approach often achieves very good result. Here we can see training and testing accuracy of AdaBoost. Then fourth, random forest. Another ensemble method, but different from AdaBoost. Random forest builds multiple decision trees in parallel, each trained on random subset of the data and random subsets of features that combines their prediction through voting. Here we said Here we set max depth equal to 5 to control the complexity. Random forests are robust and often performs very well. For each model, we report both training and testing accuracy, as you can see. Remember, we are looking not just for high accuracy, but for a model that generalize well to new data. After selecting our best performing model, in this case random forest, we use it to make prediction. We call the prediction function. We call the prediction function method on both the training and testing set. This return predicted tables 0 or 1 representing rejected or approved loans respectively. We store these prediction in y underscore pred underscore train and y underscore pred underscore test. Uh, we also look at sample predictions for first few training examples by comparing the actual level Y train with predicted labels, Y pred test, Y pred train. We can manually verify whether the model is making sensible predictions. These prediction from each basis everything we evaluate next. The quality of these prediction directly determines how well our model performs. Accuracy alone does not tell the complete story. We need to evaluate our model more thoroughly using multiple metrics. First, we create a confusion matrix which break down prediction into four categories. First, TN, second FP, third FN, and fourth TP. Here, TN represents true negative, means correctly predicted rejections. Then FP means false positive, that predicted approval but actually rejected. And FN is false negatives, that predicted rejection but actually approved. And lastly, TP means true positives, means correctly predicted approvals. Here, here we visualize this as a heat map for loan detection. Different types of error have different costs. A false positive approving a bad loan costs the bank some money. A false negative rejecting a good applicant loses the business opportunity. Understanding this trade-off is very crucial. We also calculate the accuracy score. As you can see, we also uh, calculate the accuracy score, which is overall percentage of correct predictions. It means TP plus TN divided by total, means true positive plus true negative by total. Finally, finally, the classification report gives us precision. Here, the classification report gives us precision, recall, and F1 score for each classes. Precision means of all positive prediction, how many were actually positives. This matter if false positives are costly. Then recall, of all actual positives, how many did we identify? This matter if missing positives is risky. Then F1 score, a harmonic mean of precision and recall balancing both concerns. It means the harmonic mean of precision and recall, both balancing the both concerns. Together, these matrices gives us a complete picture of model performance. Finally, let's test our model with new hypothetical consumer data to see how it performs in real-world scenario. We created a new sample with values for all 59 features representing a hypothetical loan applicant. We scale this sample using the same scalar we used for training data, as consistency is the key. The model that then predicts whether the applicant loan should be approved, means in binary 1, or rejected in binary 0. But we don't just get a binary answer, we also get class probability, which represents the model's confidence in prediction. For example, as we can see, the here the class probability is 0.89003834 and 0.10991646. It means the as the prediction is 0, means the loan applier will not given the loan. But here the confidence score tells us that the model our model is is 89.0083% percent confident not to give the loan, but only 10.991% confident to give them the loan. A prediction with probability close to zero point 0.5 on both classes indicate the model is uncertain, while probability is close to 0 or 1 indicate high confidence. This is exactly how loan detection system work in production. A customer applies, their information is fed into the model, and the system immediately provides a recommendation with a confidence score. And there we have it, a complete machine learning pipeline of loan detection. We started with raw data, cleaned it, explored it, prepared it, built multiple models, evaluated them thoroughly, and finally tested them on new data. Each step was essential. Skipping even one step could result in poor quality model. In real-world applications, spending time on data cleaning and preparation often determines the difference between a successful and unsuccessful project. This symmetric approach, EDA, data cleaning, feature selection, model building, and evaluation forms the foundation of all machine learning projects. Whether you are predicting loans, identifying diseases, or recommending products, these steps remain fundamental. Thank you and have a good day.